Okay, so I will continue with this relaxing atmosphere during my talk. In fact, so it's something. It's a kind of a remark for 45 minutes. In fact, it's due to this picture. So, as a member of this wave turbulence collaboration, I saw these pictures dozens, hundreds of times. So, power law solution. Here, this okay, and in fact, the goal of my talk is: you want power law, I will give you power law for cheap, for very cheap. So this is a joint work. This is a joint work with, in fact, so Rémi Carl, who is in Rennes, Geoffrey Beck, Ludovic Martaud, they are also in Rennes, and Geoffrey was a Simon postdoc just before he joined. Okay, so what is this picture? This picture, I think, I took it from Laurent Chevillard, who is there. Hi, Laurent. In your talk last year, I think. It's if I understand correctly, this is one of the best up-to-date appearance of this Kolmogorov power law in an experiment that is done in a wind tunnel, I think in Modane, I imagine. No, in the École Normale Supérieure of Lyon. Sorry. It's a nice power law. It's not a power law. Okay, perfect. And you, like me, heard hundreds of times, okay, there is the injection frequency bound, then the power law, and then dissipation. Okay, fine. And so now my question is completely naive. What is this function? And essentially, I also I take the opportunity to say that is this related with what you showed in Nicolas Mordant? Is it noise? This is measurement noise. Huh? This is experimental noise. So I will not have experimental noise in my theorems. But this is the only difference. Okay, so in fact, it's part of a bigger picture. And the picture is essentially, so when you are a mathematician and you see a power law function in frequency, in Fourier, it means that you have a decay 1 over k to the alpha. And it means that you have a finite regularity in Sobolev. And what is h to the s? So Nader in your talk had s equals to 1 million. So it can happen in the real life of mathematics. But it means that if you're in HS, you have a function that is essentially the integral of a distribution s times. Or said differently, if you take S derivative, at some point you end up with a Dirac or with something that is not continuous. Okay, so when you see this, you say, okay, I have a poor regularity in space. Or, of course, there is always this dissipative scale. But okay, let's see how it can be obtained. But at least if you have a straight line k minus 5/3 until k equals plus infinity, it means that you have something discontinuous in space at some point. Not discontinuous, but the derivative, I mean, so with finite regularity. Okay, and but in all the talks I heard, there is a smooth forcing. So it's not if you do not inject in your PDE something that has a discontinuity in space. I mean, maybe I don't know. Maybe in some experiment, if you do some bump in some solid, maybe you can call this. But this is another problem. But in your experiment, if you have some wave, then it is smooth a priori, smooth in time and space. So the question is how, if you have a smooth forcing of a PDE, how can you recover something that is discontinuous or almost discontinuous? So this is just this basic question that came to my mind during these 6 years of collaboration, and And you know, if you, of course, the explanations are various. So you can say, okay, it is due to some, of course, you will plot this in some probabilistic sense, you will have, etc. But here I will follow the rule of mathematics that if there is a problem that you cannot solve, there is a simpler problem that you cannot solve. And I will go down to the basement of mathematics to prove, to give something. Okay, so if you have, so I will consider something like this. So evolution equation, dtu equals a of u is nonlinear. If everything is linear, usually it commutes with the Fourier transform, and then you will have something that do not move in the Fourier. You will not have any kind of cascade in Fourier. But the nonlinearity is supposed to produce the effect. Main example here, a wave, shallow water wave, and of course, if you shake the system, if you put the epsilon, if you go from Vlasov-Maxwell down to something, this is NLS, nonlinear Schroedinger equation. And there is diffusion, and there might be also not diffusion. And now concerning the forcing. So what I heard is the forcing is localized in low frequency, for example. So I imagine some cosinus, large compared with to the size of the box or something like that. I also heard a monochromatic in time, which means that there is one frequency in time that is beating the system. But each time it is always smooth in X. And I also heard F is random. A forcing random, it is more or less like an initial condition random if you turn off the forcing. F is random. And to obtain this cascade, in all the picture I saw, there was always also some average in space, in time, etc. Okay, so in fact, this question is very similar to questions studied by people from the collaboration. So I think of all the work by Apollinario, Beck, Schroedinger, Gallagher, and Grande, which is essentially the same question. How can I transform something smooth to something that is non-smooth? By an evolution that is very nice, that exists, etc., etc. And there is also the work of Colin-Verdier and Saint-Raymond, who consider the case of where omega, so this is a monochromatic case, and you write down the solution, and you see that if you have a continuous spectrum, and this is the case because it's based on some experiment done by you, Nicola, I guess, and then you obtain a singularity in a time integral, time and space integral, which produce some unexpected time scale. And this is a kind of result that can be comparable. Okay. So these are the motivations. So I go down again to the basement of mathematics. So I will assume F independent of time for the moment. So in fact, I do not consider the evolution problem. I consider the stationary problem. Okay. So just I have a source, a PDE, question, can I have an F smooth, localized in frequency, and recover a solution, constant, of course, that is under this way. So here we consider the Fourier transform. Or so maybe, can we have this at least in a long range and a long range of frequency? Because here, of course, the game here is to have, in this picture, to have the inertial part, if you want, to be long, to be as large as possible. Yes?
Why did you take to be positive? I would have imagined if you wanted this equation, the alpha would be...
This alpha?
Oh, this is the solution, sorry. This is not the gamma.
No, this is not the gamma. Yeah. No, gamma will be 0 soon. Basement, I said, really, in the end, what can you do? You can do a polynomial of second degree, integration by part. That's all. So I choose the first one, as you will see. No, it's third degree, okay. Because, okay, so now, of course, now the one you were always, you were expected this model, the Schroedinger equation, of course. which is the mother of all the models, or the grandchild. So in fact, this has a real interest. So it's funny because this question came from another domain of interaction I had with people doing optical fibers, and they work on resonators. So this is something you have a laser impulse, and you have a comb, and after the resonator you have a discrete spectrum in the laser, and the model is NLS. And so here there is some dissipation here compared to nu. There is beta and a forcing, and the forcing is typically monochromatic, in fact, in this case. So it has a range of application, and epsilon it is the semi-classical, for example, of the size of it's related to the size of the fiber. But let me consider this. So okay, I filter the oscillations in time in this case, and I obtain this equation. This equation is a Luggiato-Lefebvre equation, especially if f is close to 1. F is close to 1, so I like a forcing that is exactly equal to 1. It's probably the best forcing ever. Is U always going to be what? In L3. Yes. Yeah. I think so, yes. What was the question? No, I understand your point. Okay. No, yeah.
So please use the button, please.
Of course, this is an excellent question, and you will see I will answer to this question. But of course, will you be in L3? Okay. Of course, this guy, paf! So not with beta equals 0. Never, in fact. Okay. Okay. Here we will go to this critical case identified by our collaborator. Okay, let's continue. So I make a change of variable. So this is just to make, I can play with the scaling. I will play with the scaling here. Okay. My goal is just to find a smooth case. I have a smooth forcing and something that is not smooth. So this equation was studied. So you have in fact, these are the solitons of the resonator, and they were studied by Mandel and Reichel, Delce and Aragus. This is another kind of topics, but they are interested in the stationary solution. It's not an empty. It's not just a mathematical question for fun. It has also a very practical implication. Okay, so let's go down again. So I take epsilon small, so epsilon is 0 at some point. And then I take nu, okay, it's complex, so I take nu equals 0. U is real, omega equals 0, and I obtain this fantastic equation, which is, of course, linked with your, with your question. The 1/3 is here. Okay, so now you see it's stupid, but there is a way to construct solution. I mean, so is there a way to construct solution to this equation starting from something like this, or someone like this? So it's usually in for example, if you do a normal form theory, or if you deal with invariant measures, etc., you're supposed to be in a weakly nonlinear regime, which means that the important person, the important guy, is the Laplace operator. And then the nonlinearity mixes the frequency, oscillating frequency, you have the resonance, etc. So here my question is just simple. Can I build a solution from the purely algebraic nonlinear solution that I have when epsilon is 0? Okay, and when epsilon is 0, I have an extremely good candidate to have power law solution, which is just given by this formula. So at some point, my talk is this formula. So the Fourier transform of the distribution x to the alpha is xi to the minus d minus alpha. So if you just look at f 1/3, and if locally f is like x to the n, okay, so it means that if you have a cancellation, then you can expect some power law solution directly. Okay, so typically, if f is positive, if you take x squared times psi, and psi is smooth and positive, so the simplest case you can imagine, then you use this wonderful formula that you can find in Hermander, for example, and you calculate that in fact this solution is this one. Now the Fourier, of course, the Fourier is a convolution, but in the convolution the worst wins, and so it means that in fact this is smooth, so it's is decaying extremely fast. So this guy wins, which means that you have an energy spectrum that is exactly like this. So it's stupid, no? But it's something that I never. So said differently, if you look to something like this, if you take the inverse Fourier, there must be a singularity in X, at least one. This is another way to say this. Okay. So now I have a slide with a few remarks and questions. So if you want to contribute to the discussion, I think it's now. Imagine that you take f as a random function. So in many talks I saw this kind of randomization, for example. Okay. Which can happen if, for example, f depends slowly on the time, and if you imagine that you have a relaxation process to some invariant solution, which is the solution of the nonlinear PDE, you locally in time, you can be like this. Okay, so I take a random function here at a scale k to the s. Then if you take f to the alpha, you calculate the Fourier transform and the expectation of psi squared. This is exactly this. This is numerically, it's completely clear. Okay, and in fact, I'm not able to prove this. So maybe someone here has some idea. The proof is that okay, f vanishes almost surely. So almost surely I can find a point where f looks like this, and then I can use essentially the discussion that I had before.
Why is it vanishing?
Because there is no average. So the expectation is 0. So, and in fact, the other remark is that I implemented this many times. If you implement this, and I remember I said to a collaborator, take very smooth, take s equal to 20. And if you take s equal to 20, this is a cosinus. Huh? So, okay, so in fact, there is a question to how randomize very smooth functions.
This is almost surely.
The cosine, somewhere. There is vanishes almost surely.
As a 0, okay.
As a 0, thank you.
So S is very large compared to alpha?
Sorry?
S is very large compared to
alpha. I don't know. This is the interest. So this is the interest of conjectures, is that you can choose what you want. But no, I have in mind alpha equals 1/3 or square root. No. So like cosinus, f vanishes in some x0, but S is large, so locally you have this, and then you use convolution argument. But how to measure it to obtain this, it's for me unclear. So if someone has an idea, I'm happy to discuss. Okay. And this is linked with the fact that essentially exponential of 40 is 0, log is a bounded function, and log is a constant. Okay, so now the question, how can you build, because it's completely not reasonable to have a solution with poor regularity to an elliptic equation with epsilon given. Well, so when epsilon is turned on, now this is elliptic, nonlinear ellipticity. If you have a solution, then it is automatically smooth. So there is an incompatibility between being smooth and being close to f1/3. Okay. So and in fact, so at least the only way that we found to imagine that something like this was possible is to kind of regularize f and be able to make the calculations. Because if you regularize, I mean, if you look at, if you imagine that locally you replace this x squared by something regularized, square root of x squared plus x4 plus delta, then it's this kind of, you don't want to prove this kind of result. It's complicated. So the trick is just to, so how can we have quasi-singularity? This is the problem. So if f is like this, so it does not vanish, then if you take the square root, you expect to have something like a power law solution. Okay, so imagine, what I mean is that here you can have singularity in the solution, but it will never give you a solution to a realistic solution to the PDE. And so here is the trick. So imagine that f is given by this guy, so delta. You see that when x is close to 0, this guy is of order delta. So it will not vanish exactly. So you can take the square root. And in fact, it's a calculation. So I cannot resist to make some calculations in the next slides. But this lemma is very, very easy. You take an alpha, you take this f, and you look at f to the alpha minus 1, because, okay, you have to remove the constant. And you can prove that the spectrum behaves exactly like this, but for a large bound of frequency. So 1 to avoid 0, because the function, there is no reason to have a singularity in 0, because you remove the 1, essentially. And 1 over square root of delta. So on a large band of frequency, when delta is small, you have the expected behavior. Of course, this is consistent. So when delta goes to 0, it goes to the calculus we had. Then this is just for fun. So this is just that you can factorize. But if you want to understand more, if you know that the solution has a quasi-singularity, then you can factorize this way and do the calculation. So this term will give you this decay. This term will give you another decay, and by convolution argument, you can say that the worst guy wins. And on the torus, you can do the same with the Gaussian torus, exponential of cos x minus 1, which converges to the Gaussian when the size of the torus goes to plus infinity. Anyway. Ouais.
How does the, sorry. Oh, thank you. I was just wondering how the delta bound changes with the width of the torus in that previous lemma.
I don't know.
Okay.
Okay, but I think in fact I have a wonderful slides. I cannot resist that. With this formula, you can. Okay, so the proof is completely easy. So x is the Gaussian, or exponential minus delta times the Gaussian. It's interesting to see this way how you can. In fact, I'm out of a strong Stirling period in my life. So the last 4 years, I realized that in fact Stirling is you can prove everything with Stirling. So all this combinatorial, etc., you just replace by Stirling, and you make you optimize the phase, and paf. Of course, it makes the days a bit long, but it works. So anyway, if you look at this formula here, so this is x will be the Gaussian essentially, an it's given by this, and using the fantastic formula of Stirling, you can have an equivalent. And the alpha, you have here 1 over n alpha plus 1. Because the question is, how can you calculate the spectrum? And this was the question, the trick. And now, if f is a Gaussian, or exponential minus delta times a Gaussian, this remains Gaussian. Okay, it's a sum of Gaussian. And I can calculate the Fourier transform of a Gaussian. So it's just, you have this wonderful exponent that come from some scaling arguments, the an that satisfies this bound, and here the n that was here is now downstairs. So you have a sum, and you can estimate this sum. So you see that when n is too large, this term will kill everybody. So, okay, so I'm sorry for this, but okay, I'm a mathematician, so sometimes I do calculations. So this is the proof, but okay, so I evaluate this by, so here I just replace the an by the asymptotics, continuous limit in y, change of variable, and I recover this psi here. Okay. So this is just I do not know how to avoid this, to calculate the spectrum of a quasi-singular solution. If you have ideas, of course, I will be happy. But this is a model, a Gaussian model, to model a singularity, a quasi-singularity. So you touch almost zero and you take square root or 1/3, and you want to calculate the spectrum. Why not? Okay. And on the torus, so to answer your question, it's the same, but you have, what's the name of this? It's written here, modified Bessel function of the first kind. So you can spend your life on special functions, of course. I will do this when I will be retired, for sure. Only studying this kind of function and the series like this is fascinating. Anyway, okay, so it continues like this. Stirling, same result. So for the torus, it's the same. Okay, so now back to the nonlinear Schrödinger equation. I want to construct solution. So now I am able to have solution to f1/3 that have a spectrum, a power law spectrum, and I want to build a solution of the true NLS. So the advantage now is that I have almost singularity, but I'm completely smooth. I am completely smooth. So it is just that my smoothness. So where is it? It's nowhere. Huh? In some sense, after this threshold, then my spectrum goes down, and I have an analytic function, in fact. So if I'm completely smooth, then it means that I can hope to obtain solution of this guy if epsilon is small enough and if I have the good sign, which is, again, this is the only technique I know to construct the solution of PDE like this one. So either the epsilon is large and I use a semilinear argument, for example, HS. So in high regularity, if the Laplace dominates, I can use a fixed point to prove that there exists. If not, I can also prove that it exists, but if I have a good sign here, and here I have a good sign, it's a defocusing NLS, which means that if I have a solution, so my solution of the linear, so for epsilon equals to 0, my solution is this one, with 1/3. And so I just linearize the equation around this solution, and I obtain this linearized operator, and here I have the good sign, which is the good news. So if I have the good sign, it means that I have elliptic estimates like this one. Of course, delta is small, epsilon is small, but it makes, I have an elliptic operator. I can completely make a fixed point using this formula. The only problem is that here, so you see, I have U naught, which is the quasi-singular solution multiplied by epsilon square. So it will work if this term is small. And if this term is small, it means simply that epsilon has to be small enough. So the theorem is like this. If I am in a regime, if epsilon is, no, sorry, this is for the linear part, okay. So I just say here that the linear operator here is invertible, so it's much simpler as the one we had in the previous talks. And due to the estimates that I have, so if I allow to lose the regularization property of the Laplace operator, I'm not losing an epsilon. So I can iterate. Okay. And to prove this, it is just some commutator lemma. It is absolutely not difficult. And in the end, I say that if epsilon is small compared to some delta, of course, capital A is something. In math, in this theorem, I do not care about the constant. And if epsilon is small enough, then I can construct a solution of this equation. And I can control the Fourier transform of this equation for a large bound of solution. So I have, I can construct a forcing that is smooth and that produce my quasi-power law solution. And okay, so extension to many cases. Adding a dissipativity here in this case, and because this is a Hamiltonian operator. So if I had dissipation, I add minus I nu. So it's more complicated. You have a system to solve, but it works similarly. As long as the nu is small enough, and okay, in some sense, if you take some random function that almost vanishes, you can do the same. If it is smooth enough, and you have stability of the time evolution. So you can prove this because if you linearize, you have it's not exactly because the stability here. You can prove an energy estimate, but energy estimate it is in H1. So in H1, you see you do not necessarily see the power law. But on some time scale interval, you can prove that you can see the power law, or in another setting with another power, etc. You can imagine too. But there is the problem is Hamiltonian. There is an energy. So in some sense, imagine that your dynamics end up with this solution somewhere deterministically, or maybe in some random process where you draw F, you let the solution run. At some point, you end up with the power law solution, and then you average. So always the worst will win. And it means that here it means that if you are close to this solution small enough, of course you will observe this solution for a long time. So of course I'm not a physicist, but at least it means that in the dynamics of this force problem, you can be for a long time around a solution that satisfy my two conditions: smooth forcing and quasi-singular solution. Okay, and now you see that you can play with many generalization of this. So if you add the monochromatic forcing, then it will change. If you make the change to the solution, you will add this omega, and you will obtain a degree 3 algebraic. So it's more complicated than degree 2, but it can be solvable. So in fact, here I boxed this equation because I think it's always interesting. You have in some sense, you have an algebraic equation that depends on x. What kind of singularity you can produce with such an equation, knowing that here you have 3 branches, for example. It's an algebraic equation, you have 3 solutions. No, 0, it depends. If you search for a real solution, you have 1, 2, or 3 solutions. Okay. And this is given by the Cardano formula. So here I just recall the Cardano formula. You make the idea is really nice, but okay, you just go to some equation of second degree for the cube, and in some sense you look at the function. So you have cases. So imagine that in x, for a fixed x, you have such a condition like this on the forcing. Then you have the real solution, and the real solution must be smooth. It is the one that go across 0, and if you go across 0, no problem. But if you are in the other case, in the other way, then you can obtain some some quasi-singularity. So maybe just I will draw some picture. It will be easier. But if this is something like that, and essentially this one is always smooth, and this one is can be you can obtain a quasi-singularity. This is what happens if you solve an equation, and this is moving with x. So okay. And so this can be generalized, and you have, in fact, in this other case. So in this other case, I will explain it later why it can be interesting. So if you have q squared smaller than p cube, then you expect, in fact, the singularity will be in this arccos function. So arccos. Imagine that you have something like this. Okay, so r is smaller than 1, and okay, someone who is smaller than 1 is a cosinus of something, and you take the arccosinus of the something in the Cardano formula, but it has to belong to 0 pi. So the singularity comes from the arccos and the fact that in fact you are not following the Riemann surface as a parking, but you are facing the arccos, so you expect another power law. This is the time remaining, right? Okay, I guess. Okay, so this is the solution, the general solution that you have, and in fact, if omega is not 0, generically you expect not the one I showed you, minus 5 thirds. Ouais. Ah oui, d'accord. OK, j'ai 13 minutes. Merci, thank you. But you expect something like this, more generically for a problem with forcing in omega. And in fact, you can construct someone like this. So again, in this regime, you have a wonderful forcing that is monochromatic in time and Gaussian forcing in x, and you recover something that has a power law with the good condition, with the good boundary conditions. But the problem is local in x. So okay, and of course, for those who do not believe in mathematics, I show some numerical examples. So this is just the solution in the case where I have no chromatic forcing. So this is the first case. So delta is the size of the quasi-singularity, and you see that when delta is going to 0, you're going to the power law solution. So it's a stupid way to construct the picture of the second slide. So it's two lines in MATLAB, but so I like this idea, but maybe I'm the only one who laughs. But okay, and so this is for epsilon equals 0, and now this is I fix delta, and I let epsilon goes to 0, so the viscosity goes to 0. And again, so here if my viscosity is too large, it's not clear if I have a good power law, but when epsilon goes to 0, so in this kind of semi-classical regime, which can be seen as a scaling of the solution, it's kind of a concentration of the solution. So it shows that it converges. Okay. And this is the other one. So the other case is when so this is for the second type of singularity. So the case given by the theorem that is here. Okay, and so here it's not here d is 1, so it's 1 over xi 2 and not 1 over xi 5 thirds. It's funny that it's 5 thirds in this case, but for the NLS equation in 1D. Okay, anyway. This is not the same solution, of course. It is just... Okay, so now we are happy with NLS. So we try to go to fluid. And so here this is, in fact, there is one case where you can do the same. It's a game, but it's for shallow water. But here it's a bit different. So so here it is an example. So imagine that you take the shallow water equation. So h is the height, and there is no z, by the way. Z equals 0 in this case. But or you can put it in the forcing, in fact. But okay, so you have the shallow water, and you can have some dissipation. And here the difference is that you have a constraint. H has to be positive. No empty lake are tolerated, which is logic. And in this case, so imagine that you have a forcing. So now I'm talking in front of my physicist friends, and so I'm not, but I'm not sure if this is the correct modeling. But imagine that some force is coming, so you're traveling. So like, it's like a tsunami, or if you are more optimistic, a surf. Okay, so a wave coming or something coming like this. Okay. Of course, so you make the change of so this plays the role of the monochromatic forcing of NLS minus omega t. This plays the role of the forcing of NLS, except that now it's just a traveling solution. So you make the change of you make the change of coordinate, and then you obtain minus omega dx, and now it's extremely. I mean, you make some change of variable here, which in fact appear in the algebraic solution. So u equal. Yeah, z is 0. No. But I mean, you can also you might, this I don't know. You might put this in the F and G. Okay, this the story of this picture is that I just took a code of a friend of mine, and then I realized that there was a z, but there is no z for me. Okay, it's a good question. I mean, to put the force in the z. You can also be sailing above something that is okay. So why not put the force in the z? But I don't know. What I say is that just I end up with something like this, and now because I'm 1D, I can integrate in x. In 2D, it's more complicated. You cannot really do this. You have to you have something that is not purely algebraic, because in the end here you end up with if nu equals to 0, you end up with an algebraic system. In 2D, you have something more complicated with it's a pseudo differential operator, and you cannot really identify some algebraic structure that could produce this kind of singularity. Okay, but you can integrate always this function if you integrate f and g. So now you have a boundary condition problem. So which means that there might be a tsunami like this. But at this level of for this talk, the thing that is funny is that now I have an algebraic problem, which of course is the same with the same normalization P and Q. P and Q depends on x, and I have a sign condition on the solution. And if I turn on the viscosity, then it's not that easy. It's not only a Laplace operator. It's a nonlinear viscosity. So numerically and also from the theoretical point of view, it's less clear, of course, that NLS. But at least for nu equals 0, you can construct a solution. And if you look at your Cardano formula, then you have some condition to have h0, you have some condition, and then I will try to just give you some conclusion. So the conclusion is that here the condition to have this h positive, which is required to have a solution of shallow water equation, it makes that you cannot be in you cannot obtain the smooth solution, and you can play, and we played a lot with these kind of things, and this is an example where here you see that P is smooth, so X is always like a Gaussian. Q is also smooth because there is this. but you can end up with solutions that are admissible under this form, but unstable. So this is clear, completely unstable. So we found first these solutions that are unstable, but finally this solution with where you follow one branch, one specific branch of the algebraic solution, and you can be admissible and stable. And so at least again we have one example of something that produces a quasi-singular solution, and that is so stable that you can then turn on the viscosity. So these are the calculations made by Ludovic Martaud. It's an ongoing work, so it's more difficult because you have to use finite volume, etc. So for NLS in 1D, you use Fourier, and then you have machine precision calculation almost. But here it's much less clear. But here, at least it means that we obtain solutions for new strictly positive, so with dissipation, and they converge toward the good thing. This is for the velocity, and this is for the surface elevation. I will stop here. I think it's fair. Non, mais c'est bon. And I thank you for your attention.
Thank you. Questions?
It's very interesting, but I was thinking you were assuming that the function was a single power, whereas there's evidence, for example, from convection that there are overlapping and subdominant scaling laws at different stages with relative to the control parameter. Would that greatly change your view?
In fact, so power. In fact, what I just say is that if you take something where you have here a linear operator and anything nonlinear, the question is how can I base my solution on the solution given by this? Now you see, what I just say is that if you're just a very nice order 3 polynomial, I have 3 branches of solution, and I can construct various kind of solution depending on the branch. So imagine that now F is a system or something much more linear. I have absolutely no idea. But for sure, there will be a Puiseux-like singularity always. And this is based on this. And this, the fact that you have fractional powers when you have branches of solution crossing, this is, I think, completely typical in any kind of nonlinear algebraic solution. And so, okay, now you can imagine to have the same at a much more abstract level if you have a pseudo-differential operator like this. But this is too complicated for me, clearly.
Other questions? Don't be shy.
Non, c'est bon.
More questions. So thank you again.
Erwan, sorry.
A question.
Erwan, how stable is this mechanism under perturbation?
Sorry?
How stable is this mechanism?
It's stable if you start
Under
small enough.
perturbation.
Small enough.
Cioè, if you add another nonlinear, if you add the quintic nonlinearity, you change this, or you change the dispersion relation. So can you build a solution like this perturbatively?
I think it's an excellent question, but we can check. So I don't know if you have U3 equals G, and if you do epsilon U5. Okay. Is it smooth in epsilon? Knowing that you have, in complex, you have 3 solutions. I don't know. I mean, not now in front of all of you on the blackboards. So for me, everything that is really nonlinear, like square root, like a solution of algebraic PDEs, this is something that is not stable because you have branches of solutions. So how can it be stable? But imagine that you are visiting the space, the phase space. You can end up sometimes you find a solution like this.
I have a physicist question.
Ah, yes.
You. Okay, I have the microphone. Now, since at some point you mentioned cascade, so this was a huge error actually. No, I'm kidding. So have you looked at if your quasi-singular solution has some fluxes of some observable? There are cascade. Cascade is not only the power law. No, cascade is
interesting.
In physicist's view. If you have a
but the question you ask is, of course, the most difficult. This is a problem with physicists. So,
you are a great physicist. I have an anecdote if you want. You are one of the greatest physicists, actually. So Landau. This is an anecdote by one of the greatest mathematicians, by the way, Sinai, who was in Princeton, by the way. And he mentioned that Landau said, I'm the second greatest physicist in Soviet Union. The first one is Jan Frenkel, since he is able to do everything with the algebraic equations. Sometimes I must use first-order differential equations. So you are one of the greatest.
Thank you, thank you. Thank you very much, I appreciate. So as my friend Landau said, no, so the question you are asking is, I have built some solution of the stationary problem. Where is it? Okay, somewhere here. Okay, I have a solution of this stationary problem. The question is, if, okay, it's stable, but to be stable, I have to start close to this singular or quasi-singular solution. So the difficult question is, if I start with an extremely smooth solution, can the dynamics send me to this place? And this is completely unclear. Completely unclear. You know that if epsilon is small, I think in the something by Kukshin, no? He proved that you can observe some. I'm sure you can do large deviation, no, with epsilon small or something like that. Alberto, no. Anyway, I think if epsilon is small, you can expect to have some significant exchange of energy. Okay, some cascade. Okay. But the question is where do I end up? And this is. Unexplained. But so maybe if there is a message, this is this one. So why not try to construct solution from the algebraic equation and then to try to go from another path to a singular solution?
No more questions. So thank you, Erwan. And
thank you.